Resonance and formal charge. Some molecules have more than one valid Lewis structure. Does anybody know what the name of O3 is? It's ozone. So if we look at a Lewis structure for ozone, we have 3 oxygen atoms. And yes, oxygen would prefer to be terminal, but somebody's got to be in the middle here. We're not going to do stuff where we have ring around the rosy. We're not going to make triangles or squares or anything. We'll save that for OChem. So the 3 oxygen atoms are just going to have to be in a row. Each oxygen atom has 6 valence electrons. There's 3 of them, so we've got 18 valence electrons. So I've already got 2, 4 on the bonds, 6, 8, 10, 12, 14, 16, 18. So there's my 18 electrons. 2 atoms have octets, 1 doesn't. So what do? Make a double bond. So I'm going to take a lone pair from, that was kind of a messy one anyway. I'm going to take a lone pair from that central atom and have it share with this guy over here that doesn't have 8. So now this oxygen has 8 valence electrons. This one has 8, 2, 4, 6, 8, and this one has 8. It's an octet. Is there another way we could draw that? Why is this oxygen having a double bond with the center one? Why not that one? Because we happen to draw it that way, that's all. These structures are extremely similar, but they're not exactly the same. Because this is an oxygen atom having a single bond, and over here, that same oxygen atom has a double bond. So these are not exactly the same. If we study the characteristics of an ozone molecule, the Lewis structure here is predicting that we've got a single bond and a double bond. Experimentally, we know that these 2 bonds are the same. There's not a double and a single. You can tell because the length of the bond would be different. Double bonds are shorter, but both bonds have the same length. So what actually is happening in nature is that it exists as an average of this and this. So you could think of it as being a 1.5 bond between these 2 oxygens and a 1.5 bond between those 2 oxygens. How do we draw that in a Lewis structure? We don't. You can't. So what we do is we draw both of the structures and then we put a double-headed arrow between them. This double-headed arrow, I was actually supposed to draw this whole thing down here. I didn't realize that. The double-headed arrow tells us that we have 2 resonance structures and that the actual molecule is an average of those. Resonance suggests resonating going back and forth, doesn't it? That's not what we mean. We do not mean that that this bond is moving back and forth, and sometimes it's like this and sometimes like that. It's an average. Any questions? The actual structure is a resonance hybrid, an average. And to help us understand this, we can think about dogs. Okay? So say you had a German Shepherd and what is that, a Golden Retriever? And, a male and a female, and they have puppies. And so the puppy might look like this. It kind of looks like the German Shepherd, and it kind of looks like the Retriever, whoops, but it's not exactly like either. But it also isn't going back and forth, half the day it looks like a German Shepherd, and the other half of the day it looks like a Golden Retriever, right? It's always the same, but it's kind of an average, a composition of both of them. Does that make sense? So that's how these resonance hybrids are. This is about the best you can do, with a dotted line and a single line, so trying to indicate a 1.5 bond. This is one of the limitations of Lewis structure. It doesn't deal well with these. Because in the Lewis model, bless you, the electrons are localized. We have to say these electrons are on this atom or they're in a bond between these two atoms. But an actual molecule isn't limited by that, and the atoms can be the electrons can be delocalized. That results in stabilization, a lowering in potential energy. It's called resonance stabilization. And it's very important in certain situations. So that's resonance. Any questions? So we'll encounter problems like this. This is write a Lewis structure for the NO2 minus ion. That's the nitrite ion. Include resonance structures. So the first thing you do is just draw a Lewis structure. Forget about the resonance until after you've gotten a good Lewis structure. So NO2. We've got a nitrogen and two oxygens. How are we going to connect those? We want to put the oxygens on the outside because they're more electronegative than the nitrogen. So we'll put the nitrogen in the middle and put an oxygen on each side. Molecules often end up being symmetrical. Then we figure out number of electrons. So we have two oxygens. They each have 6 valence electrons. How many does nitrogen have? 5. And that negative charge says we have to add 1 electron. So we've got 18 electrons to hand out here. So I've got 2, 4 for the bonds, 6, 8, 10, 12, 14, 16, 18, and I've run out. Oxygen, nitrogen both have octets. This oxygen does not. This nitrogen has an octet, and this one next to it doesn't. So nitrogen's going to be a stand-up sort of person and share a lone pair with the oxygen so that everybody can be happy. I wish it was this easy to make everyone happy in real life. So there we've got 18 electrons in the diagram, and we have an octet for everybody. What's missing? The charge. This is an ion, and so we have to indicate the charge. Okay. Now that we've got our Lewis structure, we can look for resonance structures. The way I think of this is look at this, and it's generally going to be double bonds or triple bonds that could be with other atoms. So here, nitrogen has a double bond with this oxygen, and this oxygen saying, hey, why does that oxygen get the double bond, right? They're kind of whining. Why don't I get one too? Well, and the truth is that this would be a resonance, and so we draw the other variation with the double bond to the other oxygen and a single bond to this oxygen. And again, we have to show the charge. I didn't intentionally move those electrons from the bottom to the top. It doesn't matter where you draw them. But now we have the double bond with the oxygen on the right, and this one double bond with the oxygen on the left. So these structures are extremely similar, but they're not the same. And then we draw a double-headed arrow in between, and that's the two resonance structures. Some molecules will have 3 or 4 resonance structures. And so the actual structure of this molecule has like a 1.5 bond between the nitrogen and each oxygen. The electrons are delocalized, they're spread out over the whole molecule or the ion. And we'll see with our more complicated bonding theories that those account for this delocalization. Yes?
So you say that ion has 1 or 2 resonance structures?
This has 2 resonance structures. So 2 resonance structures mean it's an average of 2 structures. 3 resonance structures would be 3 different structures. You can't draw a third one here because there's no other place to put a double bond.
So there will be no 1 resonance structure?
If you only have 1 structure, it can't be resonance. There can't be resonance. You have to have 2 or more. Yeah, good question. Sometimes we can draw a couple of different Lewis structures that look great on paper. And we're like, well, which one is it? How do we tell? And so as sort of an easier way to identify the better one, we've got this idea called formal charge. This is a fictitious thing, okay? It's sort of like oxidation state. It's something we made up to help us keep track of stuff. The actual atoms and electrons don't know anything about this. So the formal charge of an atom in a Lewis structure is the charge it would have if all the bonding electrons were shared equally between the bonded atoms. It's a fictitious charge. We calculate this ignoring electronegativity and other stuff like that. So the way your book explains it is this way. The formal charge is equal to the number of valence electrons minus the number of bonding electrons and half of the bond, minus, yeah, that. If that makes sense to you, great, you use it. I don't like it. I'm going to show you what I think is an easier way. So rules about formal charges. The sum of all formal charges in a neutral molecule is 0. The sum of all formal charges in an ion equals the charge of the ion. Small or 0 formal charges are better than big ones. And when formal charges cannot be avoided, the negative formal charge should be on the most electronegative atom. So let's look at an example. Okay, so this is hydrogen cyanide. So I'm going to, it's drawn up there, but I'm also going to draw it down here. So you can draw two different Lewis structures for hydrogen cyanide. Now, the rules I gave you, I would hope that you would pick this one. But how do we know that that one's better than this one? Everybody's got an octet. What's the difference? How could we tell? We tell using formal charges. So this is how I think of formal charges. You draw a Lewis structure, and then you say, okay, that's kind of like a family or a marriage or something, and what if we divorce, we break up this family, and we're going to split everything evenly? So we look at this triple bond, and we say, okay, oops, just cut it down the middle, share it. Well, there's an electron on each side of those bonds, right? So there's 1, 2, 3, 4, 5. There's 6 electrons in there. So when I look at carbon, well, and we got to split up this one too. So then for formal charge, what we're going to do is we're going to look at, let's start with the carbon. We're going to look at the carbon and say, well, if carbon was all by itself, if it hadn't gotten involved in this thing here, how many valence electrons does carbon have? 4. So carbon by itself has 4 valence electrons. In this structure, when we cut everything in half, how many valence electrons does it have? 4. So 4 minus 4 is 0. That's good. Nitrogen. How many valence electrons does nitrogen all by itself have? 5. And in this structure, when we've cut things exactly in half, how many does it have? 5. So 5 minus 5 is 0. Oh, this is looking good. How about hydrogen? Hydrogen has 1 electron by itself, and when we divide this up, it has 1, and so it ends up being 0. I'll just give you a clue right off the top. Hydrogen always ends up with a formal charge of 0. Just does. So formal charges of 0 tell me that's a great Lewis structure. Let's look at this one over here. Again, we're just going to cut everything in half. Let's look at the nitrogen. So nitrogen by itself, before it got involved, had 5 electrons, valence electrons. It got involved in this molecule, and now we're dividing it up. How many does it have? 4. So 5 minus 4 equals 1. Carbon, before it got involved, had 4 valence electrons, and after this gets broken up, how many does it have? 5. So that's -1. And then hydrogen, as always, ends up with 0. So here we have a formal charge of +1 and of -1. But we can also draw a Lewis structure where they're all zeros. Formal charges tell us that this is the correct Lewis structure. There's reasons behind this. Formal charge is kind of like a weird trick that works. Sometimes you can't avoid formal charges, but then you pick the one where the formal charge, the negative formal charge, is on the more electronegative.
Which one is the best one? One that has 0 or?
Yeah, we want to have 0. So if you think of that, these guys came into this arrangement. Maybe it's a business. A divorce doesn't really work very well because it's not just 2 people. But this is some sort of business arrangement. And they each brought in their own resources, their own valence electrons, and they made this molecule. And now we're going to imagine, how's this going to work out if we chop all the shared stuff in half? What would they end up with? If they end up with what they came in with, then that's really good. The result here is that nitrogen is lost an electron and carbon has gained an electron, and that's not so good. Okay, so let's do some examples. You can look up here and see how the book says to do all this math. I like this better. Just you draw the Lewis structure, you chop things in half, and you look at it. Okay, so assign formal charges to each atom in the 3 resonance forms of N2O, and they're telling us that nitrogen is central. You would not necessarily predict that, but it is. Which resonance form is likely to contribute most to the correct structure of N2O? So sometimes when you take these resonance structures and they're averaged together, sometimes one contributes more than another. If you look at my children, my husband's Japanese, I'm of Swedish descent. Guess who had more influence on what they look like? My husband, right? They all have brown hair and dark brown eyes. They look more like him, okay? So in these resonance structures, sometimes one form has more influence on the overall structure than the others. Okay, so we need to draw some Lewis structures. So we're going to put nitrogen in the middle. So nitrogen in the middle, there's got to be a nitrogen on one side and an oxygen on the other side. And then we have to count up electrons. So each nitrogen has 5 valence electrons, and the oxygen has 6, and so I believe that's 16. So 16, I accidentally changed color here, that's fine, we'll go with it. So I've got 2, 4, 6, 8, 10, 12, 14, 16. We're going to have some double bonds or something, right? Well, what could we do here? This nitrogen in the center has 8. So this is a position of strength. He's going to have to share some more. So we'll take this pair and share with this nitrogen over here. We're getting closer. This nitrogen has an octet. This nitrogen has an octet. The oxygen doesn't. So we're going to make middle nitrogen share some more. And there we go. Is that a valid Lewis structure? It is. Everybody's got an octet. So good. Could we draw other structures? We have to keep the organization here. When you're drawing resonance structures, you're not moving around what's connected. The structure stays the same. It's those multiple bonds that are moving around. So let's draw another one over here. Oxygen, nitrogen, nitrogen. So we've got a total of 4 bonds, 2 here and 2 there. What if we took this bond and made a triple on one side and a single on the other? Let's see if we could make that work. So now we've got 2, 4, 6, 8, 10, 12, 14, 16. Everybody got an octet? Yeah? What else could we do?
Quadruple bond?
Can't do a quadruple bond
Oh, yeah, it's just-
because then we don't have another bond for the other side.
Yeah, 5 of them, yeah.
Right. You got to just explore all the possibilities, though. What else can we do? Why is nitrogen making a triple bond with the nitrogen and not the oxygen? Well, let's try it. Oops. Oxygen ate too much ice cream. So we could do it like that, and then this guy's got a lone pair, and we've got 3 lone pairs on the nitrogen. Same number of electrons. Everybody's got an octet. 3 different possibilities. How do we decide which one's better? Formal charges. So for the formal charges, we're going to just cut all the bonds in half, right? Boop, boop, cut it up. So oxygen has how many valence electrons by itself? 6. And how many does it have when this organization breaks up? 6, right? So 6 minus 6 equals 0. How many does nitrogen have by itself? 5 coming in, and when the organization breaks up, it has how many? 4. So that's plus 1. And this nitrogen on the end, he also started out with 5. When things break up, how many does he have? 6. So this one's a negative 1. So I'm showing you how these are calculated down here, but we're going to learn how to do that in our heads. And so we're going to say this one's 0, this one's positive 1, and this one's negative 1. So let's look at this one over here. Break things up equally. Let's do it without writing it out. Oxygen, all by itself, has 6 valence electrons. How many does it get when this breaks up? 7. So 6 minus 7 is negative 1. Nitrogen in the middle came in with 5. Things break up, it's got 4. 5 minus 4 is positive 1. Nitrogen on the end came in with 5. Split it up, it's got 5, so this is 0. You seeing how I'm doing that? It's just like some weird, it's like learning to play Candyland or something. It's not difficult, you just have to realize what you're supposed to be doing. Okay, so this one on the bottom, again, chop the bonds in half. Oxygen has 6 by itself. When we cut this up, it's got 5. 6 minus 5 is 1. So that's plus 1. Nitrogen in the middle had 5 coming in. Things break up. It's got 5. It ends up with a net difference of 0. This nitrogen. Oh, I can't count. Thank you. Yeah, it's got 4 here. 1, 2, 3, 4. Okay, 5 minus 4. So this is plus 1 also, right? This nitrogen came in with 5, leaves with 7. 5 minus 7 is negative 2. So there's some differences in terms of formal charge, right? So this, just based on the magnitude of the formal charges, here we have 2 with plus 1 and 1 with negative 2. Nobody has a 0 formal charge. This is probably the worst. That's the least desirable. And then comparing here, the rule was if you have a negative formal charge, because we can't make something where there's 0 formal charge with these guys. We can't. There has to be formal charge. The negative formal charge should go on the more electronegative element. Which is more electronegative, oxygen or nitrogen? Oxygen. So in this structure, the oxygen has the negative formal charge. So this is the best one. This is going to be the most stable. So it's the most it's likely to contribute the most to the correct structure. The correct structure is some average of all three. Lewis structure doesn't tell us exactly what that's going to be like, but using formal charges, we can say, well, it's most like this one. These others are going to have some effect, but this is going to be the predominant. Any questions? Draw the Lewis structure, including resonance structures, for diazomethane. Here's the formula, and we're told that the carbon is central. For each resonance structure, assign formal charges to all atoms that have formal charge. So when things have a zero formal charge, we usually just don't write anything there. Okay, so we're told that carbon is central. So the carbon's in the middle. That means that the other four atoms, the hydrogens and the nitrogens, are terminal. Means they're all attached to the carbon. So there's a hydrogen and a hydrogen and a nitrogen and a nitrogen. It's actually not the only way, but yeah, this is a weird problem. After you've gone, I see chemistry as a bit like a big circle, and there's not really a starting point. People argue about what's the best thing to teach beginning chemistry students. Do you start with atoms? Do you start with units? Where do you start? So you just have to kind of jump in somewhere, and it doesn't make a whole lot of sense because you don't know the rest of it. And so you do general chemistry, and you do organic chemistry, and physical chemistry, and inorganic chemistry. And once you've gone through all the different aspects of chemistry, and you come back and you look at general chemistry, then you're like, oh, I see that now. That's why that is. And so a problem like this is going to be like really confusing for you because you haven't had OChem, right? You can't have OChem until you've had this class. And so there's some stuff that you're going to go like, well, how am I supposed to know that? Well, we don't expect you to know that. You just kind of have to mess around with it and try stuff. So that's what's going to happen in this problem. So just reading it as if I didn't know any organic chemistry, I'd say, well, that must be the structure. How many valence electrons in the whole thing? Well, carbon's 4, right? 2 nitrogens are each 5. I really would encourage you to write this down because it's so easy to count wrong. And then 2 hydrogens. So we've got 10, 12, 14, 16. 16. So then we got to put some electrons around. We got 2, 4, 6, 8. 10, 12, 14, 16. 2, 4, 6, 8, 10, 12, 14, 16. That's not going to work, is it?
Why do you put another pair on the other nitrogen?
Still, yeah.
Well, why did I give this one an octet and this one's only got 4? It actually doesn't really matter. We're going to come up short regardless. There's just not enough electrons to go around. Can we make double bonds anywhere?
No.
No, because carbon in the middle here already has an octet of electrons. So we're like, well, I did what it said. Carbon is central. That obviously can't be the whole story, right? So, yeah, carbon is a central atom, but then one of the nitrogens is going to have something on it as well. Because if we move this hydrogen over to a nitrogen, that'll make things more flexible, right? So we'll put the hydrogen over here. Now could we make a double bond? Yeah, we could. This nitrogen could share an electron pair with the carbon. So now this carbon has 2, 4, 6, 8. The nitrogen has 2, 4, 6, 8. What about this nitrogen? No. And it can't make a double bond with carbon because then carbon would have too many. So this isn't going to work either. So obviously our skeleton wasn't right. Well, let's take this and move it out. Take it off, oops, that was not the eraser. What if we do this? So now everybody but carbon is good, but this nitrogen could make a double bond with the carbon. Do we have octets now? We do. Now that one, that ended up being a mess. So let's try it. Let's draw that out a little more nicely so we can see what we're doing a little better. This is the same thing as that, right? I just straightened it out. Okay, so there's a Lewis structure for this. This is a little bit like that last one where we had 2 double bonds, and what could we do? We could do a triple bond on one side and a single bond on the other side. So let's draw it that way. So I'm going to put the triple bond over here just because I feel like it, and put the single bond over there. So now we have to put we still have 2 lone pairs, but they're both going to be on this nitrogen. So this carbon has an octet, nitrogen has an octet, this nitrogen has an octet. What's the other resonance structure? Triple bond with the other nitrogen. So hydrogen, nitrogen, triple bond carbon, single bond nitrogen, hydrogen, and the lone pairs over here this time. Any questions? Now we have to assign formal charges. So we're going to cut up the bonds and see what we've got. So this nitrogen always comes in with 5. How many does it have if this breaks up? 1, 2, 3, 4, 5. That's 5. So that gives it a formal charge of 0, right? It says assign formal charges to all atoms that have a formal charge. Well, it doesn't have a formal charge. Would I count it wrong if you put a 0 there? No, I wouldn't. Just put a 0. How about this carbon? What's its formal charge? Comes in with 4, leaves with 4, 0. How about the other nitrogen? Same, 0. And the hydrogens are always 0. So I think we've got our winner right there, right? But we have to look at the other ones. So in this one, what's the formal charge on this nitrogen? It's -1. It brought 5, it's leaving with 6. How about the carbon? 0. How about this nitrogen? +1. And then if we go down and do this guy, this nitrogen has the same situation that that one does. This is going to be +1 and -1. So this idea of formal charges predicts that this is the correct structure. Any questions? So I want to show you something that's kind of cool. So the Lewis structure for nitrogen, right? Oops, keep doing that. Just a nitrogen atom. 5 valence electrons, right? 1, 2, 3, 4, 5. How many unpaired electrons does it have here? 3. So nitrogen is going to use those 3 to make bonds. And when it does that, it will have a 0 formal charge. So you look at these guys. Nitrogen has 3 bonds and a lone pair. 3 bonds and a lone pair. It's those unpaired electrons making bonds, 3 bonds and a lone pair. So you can actually predict what's going to be happy. Look at carbon. How many valence electrons does carbon have? 4. And when we draw them, we draw 1 on each side. There are 4 unpaired ones. That tells me that carbon's most likely going to have 4 bonds and no lone pairs. And when that happens, it'll have 0 formal charge. Look there, it's got 4 bonds and no lone pairs. Oxygen, just over and over and over again, same dumb thing. 1, 2, 3, 4, 5, 6. Guess how many bonds oxygen likes to make? 2. When oxygen makes 2 bonds, whether it's 2 singles or a double, and has 2 lone pairs, it'll have a 0 formal charge.